Hello, and welcome to the first lecture of Geographic Information and Technology. So my goals for you for this week is to help you understand some of the background and history of both geographic information systems and also the science that emerged after these systems were initially developed in this whole discipline that has sort of evolved around it, and also to kind of understand the difference between the system and the science. So this is really going to establish the foundation to give you a bit of a background. So I've given you 2 readings for this week. And as I mentioned in the initial email and on the syllabus, what I want is for us to try out this platform called Flipgrid, which will enable some sort of video discussion between students. If you're signed up to be the discussion leader, I want you to start off this discussion. Everybody's going to be reading the article. But I really want you to kind of pose some interesting questions that the rest of the class can respond to, and you're more than welcome to respond again. So hopefully we can simulate a little bit of a discussion that we might ordinarily have if the course were held in person. So if you're the leader, again, I want you to put that video up first so that as the week progresses by Friday when it's due, everybody has had a chance to respond. So your readings this week are 2 things. One of them is a classic by David Mark. Was kind of one of the fathers or grandfathers of GI science, and so that's the GI science defining the field paper. And the second one is a newer article by 2 kind of younger GI scientists who are very active in the field right now, and they wrote a paper called Geographic Data Science. And so one of the things I want you to think about as you're reading and discussing this week is whether or not we even need a new thing called geographic data science. Is this just an extension of geographic information science itself, or is it truly something new? And your thoughts about where these things are going in the past and whether or not you've learned some new things. So let's try it out, and hopefully we can work out the kinks with the technology, and this will become a little bit less awkward. Okay, so today I'm going to go through a little bit of the background on the subject matter. I'm going to split it up into 2 smaller presentations, so you can take a little pause in between them, and let's get going. So give you some background about geographic information systems. So the system emerged or was developed before the science was really developed. So geographic information systems came about in the 1960s. This was really the first attempt at automated mapping. So before this, everything was done in an analog fashion. So if you did any sort of mapping, it was just done on a pen and a paper and shading the sides of mountains, just real old school. But starting in the 1960s, a couple of separate developments really started to think about how we can do mapping digitally. So one of these took place at Harvard University in their Department of Landscape Architecture and their Laboratory for Computer Graphics. So if you want to watch a little bit more, there's a small YouTube video talking about how proud they are that GIS was born there. That's debatable, but definitely one of the important first steps in digital mapping took place at Harvard. And the second one, as somebody who also gets credited as being a grandfather of GIS, is this man named Roger Tomlinson, who came up with the Canadian Geographic Information System. And so he worked for the Canadian Department of Lands, or Land Inventory Department. And one of the anecdotes I often tell in the spatial thinking, or the very introductory course that I teach to undergraduates, which some of you may have even taken, is the story of Roger Tomlinson. And one of his assignments at the Canadian Land Department was to figure out a place where they could locate a new paper mill in Kenya. And to do so, there are all these different criteria, right? So it needs to be on some flat terrain, it needs to be on appropriate soil, it can't go through endangered species habitat. So all these different spatial data layers that if you overlay on top of each other, you can look at these criteria and find the land that meets all of your criteria for the best place to locate this particular paper mill. So in thinking about this idea of what we would call that type of problem, multi-criteria decision-making problem. And so in thinking about how we could solve that digitally and not have all of these paper maps all over the place and try to overlay them, he came up with the Canadian Geographic Information System, so one of the first systems for storing digital spatial data. So he actually came up with this name, Geographic Information System, and his decision to use the word geographic as opposed to, say, land information system, which was one of his considerations, or spatial information system, was really important actually to the discipline of geography, which was facing elimination in a number of departments, including Harvard, because people say, well, it's not really a thing anymore. We know where everything is. It's kind of useless. But since he used the word geographic information system, and this starting in the 1960s eventually exploded, geographers could kind of claim this as an important area of study and design a science around it. And it really helped save the entire discipline. So we are thankful for Roger Tomlinson and using the name geographic so that geographers could really kind of stake their claim to this. So the next big development happened in a couple of federal organizations in different countries, one of them being the U.S. Census Bureau. So you know right now it's a decennial census and is mandated by the Constitution. We need to count everybody living in the country. And so it's based at an address level, and each person in the entire country is asked 10 questions. And that's again tied to an address. But before the 1970s, this was stored in a database, but there was no way to digitally map it. And so there was a famous mathematician who worked with the Census Bureau in coming up with what would become the first vector data model for storing things like streets and intersections and blocks inside of the computer that could link to that address where you took the census survey, and that would enable us to map out say census blocks by race or by income or whatever, just population density maps. And so that system that this mathematician, James Corbett, created, the acronym was DIME. You don't have to memorize it. In fact, I'm cheating. I'm looking at my notes, but it's called a dual independent map encoding. And I just bring this up because it's also mentioned in the David Mark article as a first vector format, which was a precursor for something else we'll talk about next week, the Tiger files. Again, these have all laid the foundation for how these vectors or lines and roads were stored in the computer and how the computer could understand adjacency and connectivity, which are all fundamental for how geographic information systems work. So after those agencies came the kind of the commercial era of GIS. So before the 1980s, GIS, Geographic Information Systems, were stored on large computers, taking up whole servers, but it wasn't until the 1980s where this was something that individuals could buy and store on their own personal computers. So Esri was our most famous. They hold the market share in GIS. They came out with the first personal software, and it was called ArcInfo. Today we use ArcGIS or ArcPro, and that's a descendant of this ArcInfo. So this is the old school command line GIS, which was how things worked in the 1980s. So this was developed by a guy named Jack Dangerman, who was actually a student at the Harvard Department of Landscape Architecture. So this was all developing again as a system. And as I mentioned, geographers really wanted to capitalize on the name Geographic Information Systems, which were becoming more and more popular. They wanted to bring this out beyond something that's just a software product, right? It's not so much a Microsoft Word or Excel that you're using on the computer, but they really wanted to develop an entire science and a whole discipline around this. And so this really took place in the late 1980s when this National Center for Geographic Information and Analysis was established at UC Santa Barbara, SUNY Buffalo, and the University of Maine. There was this consortium of thinkers, including David Mark, who's our lawyer reading picture you'll see on the next slide, who helped define what the science behind these systems were. And that eventually led to kind of federal standards for how we store and encode and analyze spatial data, and developed the national spatial data infrastructure. So it really kind of has blossomed beyond just this software product that we're storing on a computer to national standards in this science. So geographic information science, as you'll read in that article, again, was defined by these two gentlemen. So Michael Goodchild, very famous GIS scientist, and David Mark, whose paper you're reading there. In fact, you see my husband back there, back when he had hair. The other Dr. Demel in our department. So we both went to SUNY Buffalo, where we had David Mark as a professor. So geographic information science differs from the system in that it does not involve using GIS software to solve some problem, but rather it's concerned more with the theory, the algorithms, and the systems behind this. So it's much more conceptual, theoretical, and it involves computational innovation. So we're really advancing how these systems can be applied to solving problems. And there's various foundations, again, you'll read about in that David Mark article. Just touch upon a couple examples of what might be considered advancements in GIS science. So in the example up here of computer cartography, so digital mapping, important considerations that maybe we take for granted when we just look at a map on a computer screen and don't even think about some of the algorithm and thought that needs to go in and innovation in getting those maps to appear. So a common example could be this problem of what we call generalization. So generalization is basically simplifying some features. So here we've got this black kind of wiggly road, and it's got a lot of vertices, so that's what enables it to be very wiggly. But the problem is when you have a lot of vertices, that's a lot of data that needs to be stored in the computer, and it can cause processing to be really slow, especially if you have many of these lines. So one big problem that GIS scientists might solve is how can we simplify that line in a way that doesn't take away from the analysis or doesn't take away from the cartography. So you think of a map that's zoomed really far out of the United States, you don't want necessarily every curvy line, right? You want to simplify that as you're zooming out. And so there are algorithms that help us figure that out, right? Probably many of you have never even given much thought as you're zooming in and out of a digital map that this is something that has to take place. So if you really are intrigued by this and feel like playing around, there's a website called mapshaper.org, and you can upload a shapefile. You could play around with these different algorithms for simplifying your lines. Another example, which you probably haven't given much thought to, is this idea of cartographic label placement, right? So if you've ever made a map before and you've clicked on add labels to your map, right? And the labels just appear. And often they appear in places we don't want them to be, and you might start swearing at the computer. But the truth is, an algorithm needs to help the computer figure out where to put the labels, and the computer doesn't have a brain. We can't just say, well, don't put it on top of another feature, right? It needs to understand on top of, right, without a brain. It needs to understand not too close to a point. It needs to understand all of these spatial relationships and the fact that there's different layers and the maps can be pretty complicated, right? So the next time you scream at ArcMap when it puts a label at a place you don't know, think about that algorithm that needs to take place to automatically or do its best job in placing these labels, right? So that's something that GIS scientists will work on, those kinds of algorithms that are more efficiently or effectively place labels of all things. Other common examples could be innovations in statistics. So we all know about regular statistics that are used across many disciplines, but GIS scientists have worked on local variations, so we can map out the statistics or take into account what's going on in the local area. So that's another GIS science advancement. Or it could be in spatial modeling, trying to model complex natural and social processes, right? So hydrologic processes that need to take into account the terrain and the precipitation and all of these different things to figure out how much water is going to flow and where streams might be, right? And how do we get that inside of the computer to take place? So those are just a couple examples of things that GIS scientists work on that are sort of behind the scenes so that people can then use geographic information systems and apply it to different problems. I hope that is a little bit clear. Okay, so that's going to wrap up part 1. So now go and get yourself a new cup of tea, and we're going to talk a little bit more in part 2 about some more conceptual considerations of GI science. So thanks for bearing with me.